Okay, let's get this show on the road today. Remember, we have homework assignment due at 11:59 p.m. tonight. And do we have any questions about that homework assignment? Okay, just so you know, I probably will not be able to view email after about 4 o'clock today. So if you post something to Piazza tonight, you're at the mercy of your classmates as far as helping you out with clarifications. And today we are finishing up views, and then we are going to start into the relational algebra. On Tuesday, we're going to finish up with the relational calculus, and you'll note that there's actually a day where I said catch up, and that's where we're kind of at right now. We're going to be using Tuesday to catch up with the relational calculus, and then Thursday we'll start into the design of databases. So you may remember from last time, hopefully do, that a view is a virtual relation that doesn't necessarily actually exist in the database, but is produced from some defining query on base relations. And there's a number of reasons that you might use a view. The first is to restrict the information that someone in your organization sees. A second reason is so that you can create an intermediate result, and we'll show you doing that today, so that you simplify a query that otherwise might be very complicated to express. And we had scalar variables that allowed you to store a single value in SQL, but those variables could not store a table. So a view is in effect a way to temporarily store a table if you want to do a complicated query. And last time we talked about the fact you might have a horizontal view where you were just taking certain rows from the relation and displaying it to the user. And that might be, for example, showing the manager of branch B3 only the staff that work at branch B3. We talked about vertical views where you see all the tuples in the relation, but you only see a subset of the columns, such as an HR person able to see all the information about an individual except their salary. And then the third kind of view was one that produces or uses aggregate operations to produce some kind of aggregate value. So this particular view was one that gave a count of the number of properties that each staff person managed. And that's where we stopped last time. So where we're picking up is with some of the view creation syntax and some of the restrictions and other things that go into views. So like last time, I'm not going to spend a lot of time on the syntax, but you do create it with the create view command. Then you give the view name. And then there's an optional column list that you don't have to include, but sometimes it has more meaningful names associated with it. And then this is called, whoops, right here, this is your defining query. This is the query that determines the tuples that will be in your relation. Okay? And that's exactly the same syntax as you would use for a regular select. So same syntax you use for a regular select. Okay, give me 1 second. Let me just... Okay, so picking up. So if you omit the column list right here, if you omit this column list, then the names of the columns will be the same as the names that you use in the defining query. And we'll get to this check option later. Okay, so don't worry about the check option right now. Okay, and all that you can read later. Here's an example of, actually, let's go back and give you an example query. So, okay, so if you look right here, is that readable from the back? Okay, so if you look at this query, you can see I'm creating a view. I called it foo. And then here in parentheses are the two names that I used, hotel number and room count. As, and then my defining query is select hotel number, comma, count star. So you see hotel number matches up, and then count star matches up with room count. So count star will be called room count in my view from room group by hotel number. And this is it creates the query, and then when I show the result of the view down here, you can see I get hotel number and room count. So that's an example of creating a simple view. Okay, and then it is permissible to write queries on views. So as an example, let's go, now I set up foo, which foo gave me the number of rooms in each hotel. And now what I do is I write a query where I want to print the hotel name rather than the hotel number. So I say select hotel name, comma, room count from hotel, comma, foo, and then I join the hotel relation with the foo view, and that gives me the hotel name rather than the hotel number. So you can write queries on those views and treat them as though they were an actual table, which is kind of neat. Yes. Pardon? Yes. There's foo again. Create view foo. See, I said the two column names are hotel number and room count. As, and then this is my defining query, select hotel number, comma, count from room, group by hotel number. So that's counting the number of rooms in each hotel. Okay. Any other questions? Okay. So here's another example of a query on a view. So let me first get here. Pop back a few slides. So remember this query right here, which is where I was creating, no, that's not the right query. This is the right query. So this is a query where I was creating the manager 3 staff. So manager at branch 3 could see information related to the staff at branch 3. And then here, I'm defining, whoops, that was still, sorry, it was from staff property count. So I take it back. This was the view I created. Created a view where I was keeping track of each staff and how many properties they managed. And then here, I am selecting only the staff from branch B3 to view. Now, in order to complete this query, the query optimizer performs something called view resolution. And what that means is it has to map the query back into a query on the base relations. So it goes through a number of steps in order to make that happen. The first step is that it needs to map the column names in the select list. Okay, so these column names need to get mapped back to the columns in the defining query. So in the defining query, count was actually count star, and in the defining query, staff number was taken from the staff relation. So that is the first step, is to map the attributes, these two attributes in my query, back into the two attributes that were used in the defining query. And then I replace the names in the from list with the corresponding from list of the defining query. So in this one, I was selecting from the view, but the view, if we go back to this slide, was created from these two base relations. Therefore, the second thing that's done is that the view in the from statement is replaced with the two base relations that formed it. So that's step 2. Then step 3 is to combine where clauses. So we're going to combine the where clause from the view, which was to select all staff from branch B3, with the where clause that we used when we created the view. So if we go back again to the defining query, this was the where predicate for that view. It was a join that joined the staff with the property for rent. So what we do is we simply take the where query from the user query, combine that with the where clause from the defining query, and put an and between the two. So this is the where predicate right here. That's from the defining query. And this one right here is from the user query, or from the query on the view. Okay, then step 4, any group by and having clauses are copied from the defining query. And any order by clause is copied from the user query. Okay, and again, so here you can see that I ordered by staff number, and again we have to translate this staff number, which is in the view, back to the matching attribute in the defining query, which was s.staffNumber. Okay, so these are the 5 steps. Make sure there's not a 6th one. There is. No, those are the 5 steps that the query optimizer goes through to translate a query on a view to a query on the underlying relation. So when it's done with those 5 steps, this is the query it comes up with. And basically, there's going to be some restrictions on views, and the restrictions are that essentially when you translate the query on the view into a query on the base relations, then the query is legal if and only if the query is legal on the base relation. So basically, let's see if we go into, SQL restrictions on views is next. So I'm going to give you the bottom line on restrictions on view queries. Okay. If the, I'll say, resolved query is valid on the base relations, then it is a valid query. So if after you translate or resolve the query, if that query is a valid query over the base relations, then it is a valid query. And if it is not a valid query on the base relations, then it is also not a valid query on the view. So the ISO standard codifies these restrictions as follows. First of all, it says if a column in a view is based on an aggregate function, which is the third type of view we discussed, then the column may appear only in the select and order by clauses of queries that access the view. In other words, it can't show up in the where predicate. And it may also not show up in an aggregate query. So you can't, if you took, say, an average and then you count all the averages you took, that would be illegal. So here are two queries that should fail under the ISO standard. The first is counting the number of staff members in the staff property count. And that's illegal because this count was already computed from an aggregate function. It was a count of the number of properties that a staff member managed. So that's illegal. And this one is also supposed to be illegal because count is a aggregate function. Now, I actually, before class, thought it would be fun to see whether that was really true in MySQL, because the book said that it varies from dialect to dialect as to whether these restrictions are enforced. And it turned out these restrictions are not enforced in MySQL. So these queries work, turned out. It returns a, in this case, it returns a relation where the staff count, or it only shows staff members that manage more than 2 properties. And what's interesting about this query is that if I translated it to the underlying, to a query over the underlying relations, it would be invalid. Can someone tell me why, looking at this, if I translated it to a query on the underlying relations, why it would be invalid? Remember the restrictions? You don't. Okay. Well, the restriction on aggregates is that they're not allowed to show up on the left-hand side of an inequality comparison. They can only show up on the right-hand side. So when this gets translated to the underlying query, it would essentially be where count star is greater than 2. And since that translated query has an aggregate operation on the left-hand side, it's invalid. But it works if you put it, as I say, this query here works if you put it into MySQL. Yes, Mark?
So you're saying it's on the left-hand side of the inequality. Could you just switch it to the two?
I'm assuming that's what the query optimizer is doing, or else it's just being applying a loose interpretation of the ISO standard. So the answer is yes. Mark's question is, couldn't I just flip it and say where 2 is less than count? And he's absolutely right. But a picky SQL optimizer that is going by the letter of the standard would still not reorganize it. It would reject it. Now, I agree with you. I think a good query optimizer would simply reorganize it. It's trivial. Other questions about that? So, you need to know what the ISO standard says, because that's the so-called letter of the law. If you want to write portable SQL queries, you need to make sure you adhere to the standard. However, MySQL will in fact execute these queries on this screen. Okay, second one, grouped views. So basically, this says that you can never put a view in a join. You can never use a view in a join. And again, I went ahead and did it. In fact, I just showed you a query where I did it. Okay, right there, I said select hotel name, comma, room count from hotel, comma, foo, where, and that's a join operation. It worked. Okay, and not only did it work, but if you translate that into a query on the underlying base relations, it would also work. We went over this on the September 2nd lecture. If you go back and view the videotape for the September 2nd lecture, we went over exactly this kind of query where we were joining a relation with something that involved a aggregate, and it worked. Okay, so in fact, translating this query into one on the base relations, it's legitimate, but according to the ISO standard, it is not legitimate. So questions about that? Okay, if you're wondering why it happens, it's the same reason that G++ and GCC put convenience functions into their release, because it makes the G++ compiler more competitive on the marketplace. And that's why you have these different systems like MySQL. They will allow you to do things that go above and beyond what the standard says. But if on an exam I ask you what are the restrictions on views, I expect you to regurgitate this for me. Okay. So the next thing refers to view updatability, and it goes two ways. So if we update the base, if we update a base relation, does that update the view? Okay, and if we update the view, does that update the base relation? Okay, so this one, the updating of the base relation, it automatically updates the view. That's logical, right? You just rerun the defining query if necessary, and you'll get an appropriately updated view. So there really is no issue with updating the base relation. It should automatically propagate those updates to the view. But the interesting question is, suppose we want to update the view, meaning we want to insert a new tuple into the view. Will that propagate the tuple back into the underlying base relation? And the answer is yes, provided this update restriction is in place. So if the database can, or management system can trace that row back to the underlying base relation, it will be happy. It will allow you to update the view. So what does that mean in practice? Well, first let's show you some stuff in practice so you get an idea. So let's say I want to insert into my staff property count a tuple that says staff member SG5 manages 2 properties. Okay? The question is, should I be allowed to update the view by adding that tuple? And the question you have to ask yourself is, if I add that tuple to the staff property count, can I update the underlying base relation, which is property for rent? Okay. Well, you have to ask yourself, what is in the property for rent relation? Well, it wants to know what are the 2 properties that this staff member is managing. What is the address? What is the owner number? And that information's not provided here. The only information that's provided is that staff member's SG5 is managing 2 properties and that that person belongs to branch 3. There's no information about what 2 properties that person is managing. So the database system would reject this update. It would say, I can't update the underlying base relation based on the information you just gave me. Does that make sense? Okay. Okay. So let's say instead that my view contained actually the property numbers rather than the count. So I'm modifying the view. So instead of counting the number of properties, instead I'm keeping track of the property numbers each staff member manages. And now again I say, can I insert a tuple into that new view? Okay, so again, you think about it, you say, okay, this seems a little more plausible because if I go back to the original property for rent, it certainly has these 3 attributes. But then you start to think, wait a minute, it also requires a address, it requires an owner number, and you haven't provided any of that information, so again, the database manager will reject it because you haven't given it enough information to update the underlying base relation. Now, if these were the only 3 mandatory attributes and all other attributes in the underlying base relations were optional, then it would allow the insertion because it would simply use either null or the default value for the remaining attributes. So the question in this case came down to, are there any mandatory attributes in the base relation that aren't provided here? And the answer was yes. The answer was yes, and therefore you cannot update the view with this tuple. So those were some concrete examples, and we can actually, ISO again has a specific set of rules for if a view is updatable. So the first one is you cannot specify distinct in the select clause of the defining query. You're not allowed to specify distinct because that would take duplicates and eliminate them. And thus, when you try to map a tuple back into the defining query, does anyone remember what is, well, I'll tell you. The problem with select distinct is that it eliminates duplicate tuples. Okay? So the problem is, let's say that you insert a tuple that duplicates an existing tuple in the relation, you can't exactly, actually, I take that back. You insert a tuple and it's different. This new tuple is different than any tuple in the view. But it turns out that this tuple matches a tuple in the underlying base relation. That's a possibility. And ordinarily, you could simply check to see whether that tuple duplicated a tuple in the underlying base relations, but with select distinct, now you're not so sure because you may have projected out some of the attributes that made them distinct. So basically, it does not allow you to use select distinct. Okay? The next one is that every element in the select list of the defining query has to be a column name. Can't be an aggregate. If any column in the view is an aggregate, you can't update it. So what this says is no view with an aggregate column is updatable. Okay, that makes sense because for that aggregate, you would be inserting an aggregated value. You're not going to be able to somehow explode that value into a set of records, right? The aggregate is typically based on more than one record. So just like the property counts were based on more than one record, if I inserted a tuple that said this staff manager manages 2 properties into the property for count, you couldn't update the base relation because it wanted to know which 2 properties. So that's restriction 2. Restriction 3 says only one table may be in the defining query. So any views based on a join, union, or difference are not updatable. Okay, and finally, the defining query can't contain a group by or having clause. And essentially, it's the same problem. The group by or having clause is meant to aggregate stuff. And now you're trying to insert a tuple that's presumably based on some kind of aggregation. There's going to be no way to trace that back to a set of records that would produce that aggregation. So hopefully those 4 make some sense. And then, of course, every row you add through the view should not violate any integrity constraints of the base table. For example, if I had a relation that listed all the properties managed by staff and I could somehow insert a new property into that view, and there was an underlying constraint that says no staff member can manage more than 100 properties, I shouldn't be allowed to insert that tuple into the view because it would violate the integrity constraint on the base relation. So questions about that? Okay. Let's see, do I want to cover this or not? No, I don't really want to cover migrating. Okay. So we've pretty much already talked about the advantages of views. So just a quick summary. They give you some data independence so that you're not tied to the underlying structure of the base relations. Like a manager may only care about the number of properties that each staff manages, may not care about details. So Data independence kind of just gives each person the information they need, abstracts away all the underlying details about the base relations that are irrelevant. Currency means that any changes to the base tables are immediately reflected in the view. We talked about improved security, means that we can tailor our views to people with different access permissions so that, as an example, someone in human resources can't see everyone's salary, or staff members can't see their colleagues' salaries. They can reduce the complexity of queries. I showed you that with my foo view, which I kind of used as an intermediate result when I was trying to figure for each hotel name, I was going to get a count of the number of rooms in that hotel. I first created a view called foo that counted the number of rooms in each hotel, but the column was hotel number, not hotel name. In order to get the hotel name, I had to join my view with the hotel relation. So I used the view as a temporary result. So views can reduce complexity. Yes, Suresh?
But ISO does not allow.
Sure. But, okay, so Suresh's point was ISO does not actually allow that particular type of thing. But there's other queries I could create that would be legitimate where it was simplifying it.
Join the views.
Pardon?
We can't join the views with other queries.
Well, in ISO, but in MySQL I could. So basically, let me put it this way. Figure out what your dialect of SQL permits, and then you can use views anywhere, any way you want within the confines of that. So for example, MySQL does allow me to join views in certain circumstances, so I could use them. Okay, customization, that's kind of the same, in my opinion, as data independence. It's abstracting away unnecessary details. And then this data integrity thing says, remember I said I would circle back to that with check option way back when you can create a view. Right there I said don't worry about this with check option right now, but you can specify it, and when you specify that, let's get to the right screen. When you specify that, it ensures that a view cannot be updated with a row that violates the where condition of the defining query. So it actually means that it will check the view rather than just inserting it into the view. So without the with check option, it's like the query optimizer has the option of not checking, just inserting it into the view even though it violates the underlying base relation, it violates the defining query. It might be a legitimate addition to the base query. So here's an example. I create a view, my manager 3 staff view, where it only includes staff from branch 3, and then I try to insert into it a new staff member who belongs to branch B2. Well, it turns out that this tuple right here, in fact, is a legitimate tuple in the underlying base relation. It can be mapped back into the underlying base relation. So it's a legitimate insertion. The problem is it violates the defining query right here. The branch number B2 is not B3. So it's a legitimate insertion back into the base relation, but it violates the defining query. So what the with check option is doing is saying that I will not permit you to insert a tuple into the view unless it satisfies the defining query. If you don't include the with check option, then it will insert that tuple into the underlying base relation, and it actually won't show up in your view, right? Because it doesn't obey the defining query. Remember, when you update the base relation, it immediately updates the view. Well, this tuple violates the defining query, so it's not going to show up in your updated view. So that's what the with check option does. Doesn't let you perform what would be a so-called valid update on the base relation, but invalid on the view itself. Okay, and then the disadvantages, you can't, there's update restrictions on the views, so you can't always update them the way you would like. If the underlying base tables are altered and the columns in the defining query disappear, then you're going to have to delete the view and recreate it, which makes sense. So I don't think that's a huge problem, except in the one case shown here. If you say select star, saying I want all columns in the base relation to appear, you would think if you added a new column to the base relation, you would not have to modify your view. But in fact, you must delete the view, recreate it with exactly the same syntax in order to pick up the new column. Kind of icky, but the way it is. I would say the third issue or disadvantage with views is that ISO imposes some restrictions that aren't strictly necessary, like not allowing an aggregated view to be joined with another relation, because sometimes that when you join the aggregated view with another relation and you map that query into the base relations, it's a legitimate query. So the ISO standard is too strict. Okay, and then using views is a performance hit because theoretically you have to recreate the view from scratch each time the view is requested. And if the view is fairly large or the base relations are fairly large, that could be an issue. However, you can actually address the performance issue by using caching. And that means once you do the selection or defining query the first time, you can cache so basically what this is saying is we're going to cache the view on disk after the defining query is executed. Okay, so basically you're now treating it like a base relation in the sense that it's physically stored on the database. Anyone know what the issue with this is?
What, physically storing the...
Yeah, so what's the issue? So this is great for performance, supposedly, but what? Pardon? Okay, so you're using excess storage, although that's a typical problem with cache.
Yeah,
It's still something, yes. But there's another issue that comes up. If you're going to implement this cache, what are your concerns as an implementer? If you want to update the base relation, then either you have to throw away the cache result or you have to update the cache. So as an implementer, if you're going to cache the view, you have to then decide what you're going to do when the underlying base relations are updated. And throwing away the cache is probably not the best idea. You probably want to try to update the view. So that's called view maintenance. Okay. So for example, if you were to create a staff property rent, and this one is showing all staff members at branch B3 who who manage properties greater than 400. Okay. So now, if I'm trying to maintain this, I have to worry about what happens if I insert a new property into the base relation, property for rent. So if I insert one for SG48 and the value is, say, 800, then I need to update this view, right? I need to add SG48 to it. Now, let's say I delete it, one associated with SG37 that had a rent of $450. What does that require an update to this cache or not? Jonathan, I'll ask you. Does it require an update? Do I have to do something to the view? Do you know that for a fact? Why don't you know it for a fact? Anyone else know why? Exactly. So the person, we don't know whether SG37 is managing more than one property that's greater than 450. What's your name? Dave. So Dave said, select distinct. So the problem is it eliminated, if there were 5 properties managed by SG37, it only, because of select distinct, they all got eliminated, or duplicates got eliminated, and we only have one entry for SG37. So if we delete a tuple associated with SG37 for greater than 400, we don't know for a fact whether we have to delete it or not. The only way we know is to go through the entire base relation again, or maybe to the index, and check to see what needs to be done. Whereas an addition is very simple. In addition, we just check. Is it already there? Yes, we don't do anything. No, we add the person to the relation. So an insert could potentially be very simple, whereas a deletion could take you a lot of time or more time. So these are just the issues you have to consider when you insert and delete. Okay, and then it can get more complicated. Okay, I have a bunch of examples here, so you can just, in your free time, go through those things. But you could have something like average. So I might have an additional column, and it gives me the average value of those properties. Okay, so if I delete something or add something, that's additional work because I'm going to have to find all the properties that are greater than 400 and redo the aggregate operation on them. But a good query optimizer or a good implementation can do that. Okay, there is no reason to rematerialize the entire view. A good query optimizer or a good database management system will be able to do that update without having to do the entire calculation all over again. But I just want to point out that caching isn't a magic bullet. There's costs associated with it. And if your table, your relation is updated frequently, then you're going to have to update the cache view frequently. And you have to now make a decision as to whether that frequent updating, the cost of that updating, is worth keeping the cache. Okay, so questions about views. You get to tackle them in the next homework assignment. So have fun with them. Okay. So that pretty much concludes the discussion of the data definition language of SQL. There are some other things like transaction processing that we're not going to cover in the course because we don't have enough time. So what we're going to do next is we're actually going to circle back to the theoretical foundations for the relational database. And we already covered Chapter 4, which covered the DDL. Chapter 5 covers the formal basis for the data manipulation language or the query language. So Chapter 4 was the formal basis for the structure, or DDL. Chapter 5 is the formal basis for the query language, or the DML. Okay, so this is why 311 is a prerequisite for this course. And I will tell you that every semester in the SAIS evaluations, I get a couple comments about spend less time on this and why do we need to know it. So I'll reiterate, it's because you're computer science majors for the most part, and this isn't Palisippi State. Okay, so you should know the theoretical underpinnings for databases, not just how to use them. And we only spend about a day on it, so your suffering is limited to roughly 1 day. Okay, so there are some things that we will be covering in Chapter 5. First, very simple, there is a term called relational completeness that we will get through very quickly. And then there are two different formal languages. One is called the relational algebra, and one is called the relational calculus. It turns out, we'll see in a moment, that relational algebra is a more procedural language, and that the relational calculus is a declarative language. SQL, the query language that you use, is based on the relational calculus. It is a declarative language. It does not tell the query optimizer how to optimize things. When you start using your subqueries in SQL, you are getting more into the spirit of relational algebra, because subqueries give the query optimizer a very strong hint as to how it should optimize your query. So once you start using subqueries, you in effect are starting to drop into a more relational algebra style of programming, a more procedural style. Whereas when you use the form that I tend to prefer, which is just to use a lot of joins, you're more or less using the relational calculus version. Okay, so essentially this slide just says what I said in the last couple minutes. The one thing is the bottom point, there we define relationally complete. So it is based off of the relational calculus. So it's any language that produces a relation that can be derived using relational calculus is relationally complete. Why is that important? Because if you're creating a relational database system from scratch, admittedly not something you're likely to do today since Oracle and Microsoft dominate the market, but should you decide to do so, or in the case of Microsoft and Oracle, as they do things, they make sure that the language they use is equivalent to the relational calculus. Okay, that's same thing as when you create a programming language, saying that it is equivalent to a language accepted by a Turing machine. C++, when you get right down to it, if you tried, could be converted to a language over a Turing machine. Same thing here. Can you reduce a language like SQL? Can you map it into the relational calculus? The answer is yes. SQL is relationally complete. Okay, so we're first going to talk about the relational algebra, which most of you will be more comfortable with because you are, in fact, more comfortable for the most part with procedural operations. So this first bullet is just saying that no side effects. If you say A equals A union B, actually, take it back. If you simply say A union B, that will not modify either of the underlying relations. It will create a new third relation with the union results. It will not add B to A, nor will it add A to B. So that's point one. It doesn't, every operation has no side effects. Second one is that the operands and results are both relations. So it is closed in the sense that any operation you perform will produce a new relation. That's point two. Point three is that you can nest expressions just like you do in arithmetic. And because each expression produces a relation, it's closed. Okay, you start with two relations, you perform an operation on them, it produces a relation, therefore it's closed under the set of operations provided by the relational algebra. And relational algebra is relationally complete. It can be mapped into the relational calculus. Okay, when the original developer of the relational database, COD, devised the relational databases, he defined both the relational algebra and the relational calculus and proved that they were equivalent. Okay, there are 5 fundamental operations in relational algebra. Selection, you saw that. It selects rows from a relation. So a selection is a restriction on a relation. It's the where clause. So selection is the where clause that you have seen. Okay, projection is a vertical filtering of columns. It says these are the columns I want. It is what follows it's the column list in your select statement. When you say select column list from, the projection part is right there where you give the column list. It's a vertical slice. So the projection is a vertical slice of a relation, and a selection is a horizontal slice of a relation. Third operation is the Cartesian product. Remember, that's essentially just taking all combinations of tuples from two relations and putting them together. Union is the fourth, set difference is the fifth. Notably missing from this list of 5 basic operations is a join, which is seemingly a fundamental operation, but in fact, you can get it from Cartesian product and selection. We'll see that in a moment. You can get intersection from set difference. We'll see that in a moment. And you can get division from a complicated set of Cartesian product and division operations. So the relational algebra, typically when you see a language like SQL, joins, intersection, and division is in the standard. But strictly speaking, it's unnecessary because those 3 operations are derivable from the base set of 5.
You said, did you say you can get division from Cartesian product and division?
I'm sorry, set difference. I probably did, but I meant you can get division from Cartesian product and set difference. And projection. So 3. Yes, I think those 3. I don't think you need union or selection. Okay, but you'll see that. Okay, so this is just a pictorial example. So as you can see, selection is a horizontal slice, projection is a vertical slice. The Cartesian product is like multiplication because it takes every combination of the domain or the values from each of the 2 relations. Union, it just essentially is a concatenation of the 2 relations with a removal of duplicate tuples. Remember that a relation can't have duplicate tuples, so at most you'll have for each tuple one duplicate in the other one. So, but at any rate, it eliminates duplicates. Intersection is just the common tuples between two relations. And set difference is the ones that you get when you, in effect, subtract off, in this case, r minus s. In effect, you subtract away the tuples that are in S, leaving only the tuples that are unique to R. Or another way of saying it, set difference is the set of tuples in R which are not in S. But subtraction is just like regular, if I said 7 minus 3 equals 4, okay, same thing. If I have 7 elements in R and 3 of them overlap with S, in the end I only have 4 elements in R.
So it's basically R minus the intersection of R.
That's right. It's R minus the intersection of R and S. Okay, then you've already seen a natural join. So this is, we'll see in a moment, but that's the symbol they use for a join. A natural join, what's a natural join? Someone refresh my memory. It's a simple, well, it's not, a simple join is a equality join. So a simple join is actually a join that just involves equality testing. Pardon? It's a join on the common set of columns.
You have performed the example using the simple join and natural join, same thing.
In this case, it is. A join, it's a simple, actually, it's a simple join. Whoops. It's a simple join on the common set of attributes. So simple means it's doing equality testing. And it's the common attribute. So here the common attribute is B. Okay. And by common we mean attributes that have the exact same name. Okay. This is called a semi-join because it only includes the tuples from one of the two relations. So it's as though you joined two relations but kept only the column names from one of the two. So in this case, we joined T with U but only kept the columns from T. So it's a semi-join because we, in essence, discarded all the information from U. But you see, we only included in the result here the tuple in T had to match some tuple in U. Otherwise, like B did not get in because it did not match any tuple in U. And you might say, well, what's the use of that? Well, let's say this is students, and this is courses that the students are taking. Let's say I wanted to get all students who are taking CS 140. All the information about students who are taking 140. That's a semi-join. I don't care about any information in the courses relation once I have done my join. All I want is to know which students are taking CS 140. Once I know that, all I care about is the student information. That's a semi-join. Okay, we talked about outer joins. What is an outer join?
Left and right, it leaves either left side. Like if you say left outer join, that it includes everything from left side.
That's right, Suresh. So it means, in this case, it's a left outer join, so all the tuples from T are going to appear in the result, even if they don't match a tuple in U. So in this case, B shows up in the result, even though it does not match any tuple in U. Okay? Division is the one that I always have the hardest time getting my head around. So let's just start by an example from, say, numbers. Let's say that I want all the numbers that are evenly divisible by 24. Okay? What that essentially means is that I want all numbers that are I want all numbers that are evenly divisible by 2, all that are evenly divisible by 3, and all that are evenly divisible by 4, right? Because if I say x divided by 24, that's comparable to saying x divided by 2 times 3 times 4, which are the factors of 24. So I'm saying that in order for x to be included in my set, it needs to be divisible by each of the individual factors of 24. That's kind of what set division is like. It's saying that in order for, if I say r divided by s, the only way something from r appears in the result is if it matches every single tuple in s. So here, it's an example, v divided by w. We have w consists of 1 and 2, so we'll end up, these two completely match everything. These two completely match everything. In some sense, they are divisible by both the 1 and the 2 and b, so both a and b show up in the result, but c doesn't show up in the result because it's not, quote, fully divisible by s. And then you say, okay, so what is this part that shows, this part that shows up? Think of what shows up as what is left when you divide the number by it. So if I had 72 and I divide it by 24, what's left is 3. So it's kind of what the quotient is. So if this is R with these columns, say A, and let's say this is B, C, D, and this is B, C, D, when you divide, it eliminates the common columns, and what's left is the so-called quotient, which is any of the remaining columns. Okay, and then down here you have the so-called remainder. Okay, if I had something like A3 and A4, this is a remainder because they are not part of, they're not part of W. They're a remainder. It's as though, and now I know it gets a little breaking down a bit, but let's say I divide 77 by 24. It's like 3, and there's a remainder of 5, because 77 equals 77 minus 5 divided by 24. So it's the same idea here, or think of it as, no, that's wrong. What I wanted to say was 72 plus 5 divided by 3. So this is the quotient, this is the remainder. In some sense, that's what we're talking about here. This is the remainder part. It's additional cruft that's not part of the final quote. Well, when you do the division, it's like the fractional remainder that you throw away.
Say one is also remainder.
No, right here, that's not. It doesn't even, it's like it's less than. So think of this one as something less than 24. It doesn't have everything. So for example, 17, or let's say 12. 12 doesn't do it. It has the factors 2 and 3, but it doesn't have 4. So think of this tuple as being less somehow, less than 24. It doesn't have enough of the stuff. So the remainder is for those sets of tuples that have too much, like those that are greater than 24. The ones that don't make it in are the ones that are less than 24. They don't have enough of it. Okay? For me, it helps to think of it that way. Okay? It took me several years to come to think of it that way. If that doesn't help, then you'll have to get your head around it some other way. But that's how I get my head around it. And it makes sense to me. Okay. So we're going to go through the easy stuff first, and we'll stop when we get to joins. You need to know what the mathematical stuff looks like, the mathematical symbology. So for a selection operation, the where part, remember, this is the where part. The thing is, great, I forgot before I came here to think. It's basically an O with the thing over the top. I forget the Greek. Sigma. It's sigma. So you write something like sigma, and then the where clause is a subscript. So if you were doing this on a word processor, the predicate is a subscript. So sigma, subscript, salary greater than 1,000, and then in parentheses is the relation name. Okay, and I will be fine. Do I have a further example? No. I'm fine with you saying and, say, name equals BVZ. I think technically you would be using that for and that for or, but I'm not going to be picky. So those are the set theoretic ways of doing and or. For projection, it is a capital pi, the capital letter for pi in Greek. And again, a list of column names as a subscript. So you go again into subscript mode. So for example, here we're projecting the staff number, first name, last name, and salary from the staff relation. Okay, union, pretty obvious, R union S. Remember, they have to be union compatible, meaning that they have to have the exact same set of columns. They actually do not have to have the same column names. They just have to have the same data types. Like if column 1 is a number in both cases, it works. Now, that can lead to stupid results, like having, say, a rooms relation with rooms and a, say, family with num children. Technically, you could union those two relations, yielding a completely nonsensical result. Okay, so in practice, you should use some common sense and only union relations that not only have columns with the same number of columns and same data types, but they actually semantically mean the same thing. Okay, obvious. So typically what you have to do in order to make two relations union compatible is you have to project out the common columns. So in this case, before we could union branch with property for rent, we had to union out the one common column, which was city. Actually, address was also a common column, but in this case, we were just looking for the set of cities in which we either had a branch or a property for rent. But it would have been equally valid to say, project the city and address and city and address. And you could say, oh, but it would also have been equally valid to project, to do a union on the whole thing because all three columns have the same domains, but clearly ID is meant to be different, right? So it's kind of stupid to union on the ID. whereas city and address in some sense cover the same domains and mean the same thing. Set difference, also pretty obvious, and union compatible. Not even going to bother with the example, you can look at the slide. And this is the last one we'll consider today, set intersection. Remember I said it was not one of the fundamental operations. That's because you can actually express it using set difference. Okay, so here's the picture. Here's R right here. Here's S. Okay, so if I subtract S from R, I end up with this set right here, which is the set of tuples that are in R but not S. So therefore, if I subtract this thing from R, I must get this, right? Because this right here can be said this is in S, this is not in S. Okay? And R intersect S in some sense is R minus whatever is not in S. And whatever is not in S is R minus S. So you can actually get set intersection from set difference. That's why it's not a fundamental operation. Okay, we'll pick up with Cartesian product on Tuesday, and we'll also go and finish the relational calculus on Tuesday. 1 second.